In today's video, I'm excited to walk you through the updated GPU virtualization feature we've added to Bud AI Foundry. This upgrade enables dramatically more efficient resource utilization, letting teams run more models on the same hardware, while reducing both CapEx and ongoing OpEx for GPU-based GenAI deployments without compromising SLOs. The majority of GenAI deployments consume only a fraction of their GPU's capability. Take a common example of running a Llama 3.8b model on an NVIDIA A100 with 40 gigabytes memory. In real-world enterprise settings, that workload typically uses just 20 to 30 gigabytes of VRAM, with 60 to 70% GPU utilization, with occasional spikes. The rest of the GPU's capacity sits idle, yet the organization is still paying the full cost of the hardware, power, cooling, and operations. This underutilization adds up quickly. In a 10-node H100 cluster, where each node costs $85 to $120 per hour, operating at 30% underutilization results in approximately $183,000 to $259,000 in wasted spend per month. Those unused resources could instead support additional workers, embedding pipelines, guardrail systems, or other model workloads. But the challenge is deploying multiple models in a single GPU is extremely difficult. You need isolation for memory, compute, memory bandwidth, driver-level resource partitioning, and careful container orchestration to ensure one model can't crash or starve another. It requires kernel-level controls and deep GPU engineering expertise, something most teams don't have. The implementation also varies across GPU versions and vendors, making it even more difficult to scale and manage in heterogeneous environments. Because of these limitations, enterprises often resort to buying more GPU cards, or for on-prem AI appliances, purchasing additional units, even though their existing hardware still has significant idle capacity. This drives capital expenses and operational costs sharply upward. To solve these challenges, we are introducing Heterogeneous GPU Virtualization, an automated multi-layer GPU virtualization system powered by our new proprietary virtualization method called Fixed Capacity Spatial Partitioning, or FCSP in short. This ensures strong resource isolation and reliable SLO guarantees, even on commodity and entry-level GPUs across vendors, such as NVIDIA, AMD, Intel, and Huawei. It enables scalable GPU virtualization with no additional management or development overhead. Let's take a look. Log into your Bud AI Foundry dashboard and go to the Projects tab. Open a project to deploy a new model. Select the model you want to deploy, and now you'll see two options. Either deploy the model on dedicated hardware or on shared hardware. With this shared hardware option that employs GPU virtualization, you finally get full value from the GPU hardware you've already paid for. Different teams, customers, or workloads can share the same GPU infrastructure while remaining fully isolated. Bud AI Foundry's GPU virtualization engine uses 3 different methods to make sure every workload gets predictable performance, strong isolation, and maximum efficiency, regardless of the GPU model or vendor. First, for high-end GPUs that already support hardware-enabled virtualization, we use multi-instance GPU, or MIG. MIG lets us split a single physical GPU at the hardware and firmware level into multiple isolated GPU instances. Each instance has its own dedicated memory, compute cores, and bandwidth, so multiple workloads can run side by side on the same GPU safely and efficiently without interfering with one another, guaranteeing SLOs without any overhead. However, most GPUs in the market today, especially mid-range and entry-level cards, don't support MIG-like virtualization. So for those, we developed a proprietary method called Fixed Capacity Spatial Partitioning. This approach virtually slices the GPU into isolated chunks with guaranteed VRAM and compute, effectively turning a single GPU into several independent virtual GPUs. Each slice behaves just like a dedicated GPU card, with stable performance and strong isolation. And finally, for older generation GPUs that can't support MIG or FCSP, we use time slicing. This is a software-based scheduling technique that rapidly switches workloads on and off the GPU, giving each one a controlled share of execution time. While it doesn't provide the same level of isolation as MIG or FCSP, it still allows multiple models to run on older hardware in a flexible and efficient way. Now let's take a look at how FCSP actually works in practice. Suppose you want to deploy two models on a single GPU, maybe a large language model for generation and a smaller model that handles guardrails. FCSP uses SLO-aware request bin-packed scheduling. That is, based on the SLO requirements for each workload, FCSP slices the available GPU resources into isolated chunks, assigning dedicated VRAM and compute to each one. From there, FCSP's process-level scheduler manages how individual processes and threads share the memory and compute inside each virtual GPU slice. It controls the order of execution and how long each process runs. The end result is two fully isolated virtual GPUs, one for each model, running side by side without interfering with each other's performance or SLOs. That's a simple two-model example. But real GenAI deployments involve many more models, and often many different types of hardware. You might have GPUs from NVIDIA, Huawei, AMD, and even Intel Gaudi. And these could be deployed on-prem or across different clouds. This is where FCSP expands into topology-aware bin packing. In this mode, FCSP evaluates the SLOs of each workload and intelligently places them onto the available GPUs, not just based on free resources, but also based on the physical interconnect layout of your hardware. It considers things like GPU to GPU bandwidth, NVLink or PCIe connections, and other topology details that affect data transfer speed and latency. By considering both the underlying hardware topology and each workload's requirements, FCSP can deploy multiple models or workloads across available GPUs in the most efficient way possible. This minimizes communication bottlenecks and overhead, outperforming approaches like time slicing or Hami-core, while maximizing overall performance and reliably meeting SLOs. So that's a quick overview of how GPU virtualization works inside Bud AI Foundry. Its heterogeneous virtualization layer supports GPUs from multiple vendors, as well as GPU as a service from major cloud providers. It employs multiple virtualization technologies, enabling GPU slicing not just on high-end data center cards, but on almost any GPU. With its multi-layer optimization pipeline and dynamic fractionalizing, Bud ensures maximum performance and near-perfect resource utilization, while still maintaining complete isolation between workloads. Bud AI Foundry also integrates seamlessly with modern orchestration stacks, like Kubernetes and OpenShift, and provides rich analytics and visualizations, so you can see exactly how your GPUs are being sliced, scheduled, and optimized in real time. And to make things even simpler, we've built an auto-optimization copilot that helps you fine-tune your GPU virtualization settings automatically, so you get optimal performance without needing deep GPU or systems expertise. Thanks for watching, and stay tuned. There's a lot more coming as we continue to push the boundaries of enterprise AI infrastructure.